Hey, everybody. Welcome to NET403, the AWS Direct Connect deep dive session. This is a 400-level talk, so we're going to go pretty deep into networking, and specifically AWS Direct Connect. I'm Justin Davies, and I'm a solutions architect based out of San Diego, California. I know a few of you in the room, so it's nice to see that you came to hang out. Now, I will preface this that if you're a network engineer and you eat routing loops for breakfast, such as myself, we're not going to be super protocol heavy, but we will be focusing on some of the nuances and ways that AWS thinks about networking and implements AWS Direct Connect. Now, just to get to know the audience, this isn't a test, but raise your hand if you know what's going on here, what this thing does. Awesome. You know, networking is almost always either the hardest part or the easiest part of a solution, depending on what your background is and what you're used to working with. Very rarely do I come across a true jack of all trades, a full stack engineer. So just a little more interaction just so I could feel my audience here. Raise your hand if you were a network-focused individual, a network engineer. Awesome, that's kind of what I expected. Raise your hand if you're on the other side and you are more applications-focused and systems-focused. Oh, wow, that's a really good mix, okay. Now, a little shift, and you can raise your hand twice if you want to, but raise your hand if you are that full stack engineer, or true jack of all trades. Awesome, the rare breed. This little snippet up here is actually how you apply a community to a route. And it does a lot of different things, but in the instance that we're going to talk about in a little bit, it allows us a way to manipulate the way traffic travels in and outside of AWS with a mechanism called local preference. So don't let this scare you. If you have no idea what it does, it's either because this is a Juniper config and you're used to Cisco, or vice versa. But we'll walk through some of this stuff, and we will actually spend a little bit of time going over some of the fundamentals so that we're all kind of learning on the same page. So you'll see me go in peaks and valleys of deep, not deep, deep, not deep. So what are we going to talk about today? We're going to do a level set. Like I said, we're just going to go through some of the fundamentals, make sure that everyone's got the basic constructs, VPCs, subnets, route tables, Direct Connect, VGWs, so on and so forth. We're going to talk about some new features. These are things that came out some days ago, others over the last 12 months since the last reInvent. You know, a great resource if you're not familiar with it is going to YouTube or SlideShare and looking up years past reInvents. So we use this as kind of a way to help document some of these things that were released. So we'll talk about some new things that were over that last 12-month period. We're going to talk about route manipulation, the community stuff, the local preference stuff, and how to direct your traffic in the way that's predictable and understandable. This one's a kind of a funny one. You know, raise your hand if you're a finance person. Okay, we got one, and I know he's lying. This is actually a super frequent question I get asked among a lot of customers. So I'm going to I'll speed through this one, but we're going to go over some Direct Connect billing. You know, who pays for what am I paying for, so on and so forth. And then if you guys are familiar with the Route 53 resolver service, we are going to go over some of that because it lends to some pretty unique designs across Direct Connect. And when customers have, you know, DNS on-prem, they have instances and VPCs, and they need the two to talk to each other. So we're going to go over some of those use cases. And then to close out, I'm going to leave with some open-ended questions that will help guide you in trying to figure out, you know, what does resiliency mean in your own organization? You know, what my meaning for resiliency is doesn't necessarily fit the same idea of resiliency you need. Not all applications are the same. So it's going to kind of be a template for questions to ask to make sure that you're architecting in that well-architected framework. Okay, so if you're here at this talk, you probably have one data center or branch office or many data centers across the world. You have stuff outside of AWS. You also either have or are interested in having VPCs. These VPCs are basically like your virtual, isolated, logical data center that lives up in AWS, in the cloud. Now, these VPCs live in geographic areas, and we call these geographic areas regions. For example, you may be familiar with US West 2, which is in Oregon, or US East 1, which is in Northern Virginia. Now, these regions consist of many physical data centers. And in order to give our customers the ability to allocate resources in the most redundant way possible, we group these data centers into a construct called availability zones. And an availability zone basically maps these groupings of data centers within the geographic area into fault domains that are designed to withstand the most common impact scenarios: earthquakes, flood zones, even routine maintenance. Now, I wanted to make sure to point this out because it's a super key, important thing to understand, and it's a key tenet to designing, deploying, and operating well-architected systems and applications. Now, just as you would in any data center, you allocate an IP schema in the form of a CIDR notation. You can have multiple CIDR allocations per VPC, and within that allocation, you can further subdivide the VPC with subnets. You also have the ability to use route tables. And these route tables, you can have a single route table and put many subnets in it, or you can have multiple route tables within a VPC with one or many subnets attached to it. Now, why would you do this? An easy example is the kind of 3-tier web app example, where you have your front end, maybe your load balancers, and they're sitting in a public-facing subnet. And for that subnet, you want to be able to control the way the routes work. And that one, you have a 0/0 default route facing the internet gateway. But your back end, your application servers, your databases, these are things that you don't want to have a 0/0 route. Maybe you don't even want to have a default route. Maybe you only want to have local routes. Or maybe your application server that's sitting in this private backend subnet needs to talk over the VGW, which we'll cover in a minute, to your data center. And so maybe at that point, you want to put a 0/0 route facing your data center. You do this with route tables. If you want to connect to your on-premise data center, you need to configure something called a virtual private gateway. You're going to hear me call this throughout the talk the VGW. And you can think of this as a logical, fully redundant, distributed router that sits at the edge of your VPC. The VGW can terminate IPsec VPN for workloads with a little bit more flexible performance requirements, because it's typically going over the internet. You can do these over something called a public VIF, which we'll talk about in a minute. But for this talk, we're really going to focus on Direct Connect, and we're not going to focus on VPN. Just know that with that VGW, you can also terminate IPsec VPN. And around the world, we have partners like Equinix and CoreSite, who provide co-location facilities. These are also referred to as Meet Me locations. AWS will deploy 2 or more routers at these locations that act as high-performance uplinks to the AWS cloud. You can place your routers at these locations, or you can work with the provider to give you backhaul, or maybe like a last mile connection to these facilities. AWS can also integrate with your current L2 and L3 MPLS connections, or it can be a single dark fiber connection point to point. And if we zoom in to the Direct Connect location, you'll see that there's at least 2 routers sitting at the left side of my simple drawing of a patch panel. And to order a Direct Connect, you simply log into the AWS console and ask a few questions. You can do this through APIs and AWS CLI. A lot of people that I talk to actually never really thought about this, but some customers will actually integrate their onboarding of Direct Connect and VPC attachment with the APIs, and they'll do it through their ticketing and workflow processes. So they're literally not involved. It's a self-service process through Direct Connect, just by using these APIs. You pick the location of the Direct Connect and the interface type, such as 1 gig or 10 gig. Once this is completed, we're going to generate an LOA and CFA. That's letter of authorization and connection facility assignment. And this is what the co-location facility needs in order to make a cross-connect circuit from your router to the Meet Me patch panel where we're connected to. So basically, it's connecting from your router to us. Once you have received the LOA and CFA and have made that cross-connection circuit, you're good to go. Everything from here on out is self-service. Our interfaces are already up, and we're pre-terminated to the patch panel fronting this, your connection. For interface statistics, such as light levels and errors, those can be found in the Direct Connect account. The person that ordered the Direct Connect, they can find those statistics inside the CloudWatch console. So super helpful. Now that we have the physical connection set up and out of the way, you'll need to configure logical connections. You can think of these as sub-interfaces or units if you're used to more Juniper terminology. In AWS, there are 2 different types of these logical connections that we call virtual interfaces. Everybody in this room probably already knows, but a lot of people call these VIFs. You're going to hear me refer to these from here on out as VIFs. There's a private virtual interface and a public virtual interface. Both virtual interface types are configured as separate .1q VLAN tags across the physical Direct Connect circuit. A private virtual interface is a logical connection between your router and an AWS VPC, or something called a Direct Connect gateway. We're going to talk about that in a tiny bit. A public virtual interface connects you from your router to the Amazon network edge. And it allows you to connect to services that are public services, things that you would also be able to connect to through the internet. This is things like DynamoDB, Amazon S3 object storage, elastic IP addresses on an EC2 instance. So it's just like if you were to connect over the internet, but with a high-performance, closer connection. Before diving into the details of the virtual interfaces, the VIFs, let's kind of jump back to the physical interface, because I want to talk about a couple things on that front. You have the ability to select 1 gig or 10 gig across all Direct Connect locations today. If you need sub-rate connectivity, you can also work with partners that can configure hosted connections sub 1 gig. Direct Connect supports link aggregation, lags. And this is used to increase bandwidth across a router. So you can bundle multiple 1 gigs or multiple 10 gigs into a single logical interface to increase bandwidth. In order to take full advantage of higher interface speeds, we also now support jumbo frames, Ethernet frames the size of 9001. Now, it's important to note that the whole path in your workload needs to support jumbo frames in order for this to really be any advantage. You also want to make sure that your EC2 instances, if that's the destination, support jumbo frames. Each physical interface that you order allows you to create up to 50 virtual interfaces. As I mentioned before, the virtual interface, the VIF, is essentially the .1q VLAN tag that's provisioned across that physical interface. It's at the virtual interface level that you configure each BGP peering address that is typically a /30 or /31 address. You can mix and match on the same interface through the use of the VIFs for public virtual interfaces and private virtual interfaces. And I get a lot of questions around how to handle Direct Connect in different accounts. Maybe you have a Direct Connect account and you have an application account. Same payer account, but just different accounts for separation of control. The Direct Connect account, whoever owns the Direct Connect, is able to host these virtual interfaces and assign them to the other accounts. It doesn't even have to be in the same master payer account. When these are hosted, it shows up in the other account's console as a virtual interface. Once it's accepted, they have complete control of that virtual interface. If they want to attach it to a VPC, deattach it, move it to another VPC, leave it alone, they're in complete control of that hosted virtual interface. When you want to connect directly to a single VPC, within your local region, which we're going to cover in just a minute, you will use a private virtual interface, or as we call it, a private VIF. First, you create a virtual private gateway in the VPC console, and you specify the Amazon side ASN, Autonomous System Number. Then in the Direct Connect console, you set up a private VIF. Here you're going to specify the customer gateway, your router, ASN, the peering IP, the MD5 hash for the BGP session, and the virtual private gateway, the VGW, that you want to peer with. For private VIFs, we can also auto-generate the MD5 and the peer IPs if you want that. You can have 50 VIFs per BGW. You can think of this as 50 BGP sessions per VPC. A public virtual interface is exactly what it sounds like. It's a direct peer from your router to ours. Because this is a virtual public interface, we require that you use public IP addresses on your side. You don't have to use a public ASN, but if you do, you have to have it registered. By default, we will advertise our global range of prefixes supporting all of our public services, S3, DynamoDB, Elastic IPs, so on and so forth. Your prefixes, the ones that you advertise to us, by default, are also advertised globally to all public regions, excluding China. We will not advertise your addresses outside of our global network, and we do not support any transitive routing through our backbone, which includes not advertising your prefixes on your Direct Connect link to other Direct Connect customers. If you need more granular geographic scoping to limit your route advertisements from our side and from your side, or would like to filter AWS prefixes by geography, we support bidirectional BGP communities to scope address advertisement, such as the local region, the continent, or global, worldwide. If you need to access public resources and do not own any IP addresses, we can generally work with you to provide a public IP address that you can use as on your outside customer gateway router to perform NAT. So that is also an option. Also, it is important to note, we're not going to go super deep in this in this talk, but there are other talks that are going to discuss some of this stuff, that you can connect to these public resources through your VPC with the use of AWS Private Link. Private Link is accessible over Direct Connect. So that's another option if you don't want to use a public VIF. Now, you may have heard me say earlier, local region or home region. And you may be wondering, how do we define a local region? For example, the local or home region for one of our locations in New York, core site New York, is our region in Northern Virginia, US East 1. We have other Direct Connect locations, such as Equinix Ashburn or Digital Reality in Atlanta, that share that same home region, US East 1. We basically loosely define the home region of each of these Direct Connect locations based on geography and performance. The important thing to note on home regions is that private virtual interfaces connecting from one of these Direct Connect locations to a VPC can only connect to VPCs within its local region. With a standard private VIF, you cannot connect from one region to another. For example, you cannot connect from core site New York to US West 2 in Oregon. To do this, you can use the Direct Connect gateway. I get this question all the time. Do I need to have a BGP session for every single VPC? And if I have to have redundancy, do I times that by 2? Here's another one I get all the time. How do I connect to a VPC in a different region? I have a new branch office in Singapore, but all of my data and everything that I need is in US East 1. With Direct Connect Gateway, you can simplify both of these questions: global connectivity, crossing regional boundaries, and simplified peering and VPC attachment. I see a couple of pictures going on. All of this stuff, just in case you didn't know, all of this stuff will be available on SlideShare in a matter of days and be posted on YouTube as well. So what exactly is this Direct Connect Gateway that I keep referring to and alluding to? You can think of Direct Connect Gateway as a redundant, distributed peering point that mediates and aggregates the Direct Connect peering and the VPC attachment. So in network engineer talk or in router talk, this is essentially, you can think of this like a distributed VRF or a logical redundant route reflector. When you create a Direct Connect Gateway, you specify a name for the Direct Connect Gateway and the Amazon side ASN number that you would like to use. You can think of this Direct Connect Gateway ASN as the Direct Connect Gateway's ASN. The Direct Connect Gateway is only used for VPC attachment. It provides you no benefit for any kind of public connectivity. After the Direct Connect Gateway is created, you have the ability to connect or associate up to 10 VGWs. Remember, the VGW is the logical, isolated, redundant router that sits at the edge of your VPC. The Direct Connect Gateway can be associated with up to 10 VPCs. Today, these VPCs need to be in the same account. In this model, the VPC or application accounts typically create and own the Direct Connect Gateway. if the owner of the Direct Connect, typically a network operator, doesn't have to be, was in a different account, they would host virtual interfaces like we discussed before to the destination account, the account that owns that Direct Connect gateway. After accepting the virtual interface, the VPC account owner could then attach the virtual interfaces to the Direct Connect gateway. So how does this scale? The Direct Connect gateway supports, just like we talked about, 10 VGW attachments, which means 10 VPCs. To scale beyond 10 VPCs, you need to essentially just create another Direct Connect gateway. Now, there's not necessarily a best practice of how to group these. You know, sometimes folks like to group VPCs by region. Other times, folks like to group VPCs by task. Whatever makes sense in your organizational model is what I would recommend. Personally, I'm a fan of grouping VPCs behind Direct Connect gateways per region. And having redundant tasks or isolated application stacks split across multiple Direct Connect gateways to further isolate potential configuration mishaps. This is only relevant if you have a lot of VPCs and a requirement for regional redundancy. Keep it as simple as possible. A Direct Connect gateway is similar to the VGW in that it's a logical distributed router construct. You need to apply the correct level of redundancy from your customer gateway to the Direct Connect gateway. We will handle the redundancy from the Direct Connect gateway to the VGW and VPC attachment. Each Direct Connect gateway supports up to 30 virtual interfaces per account. At a minimum, you should have at least 2 virtual interfaces, BGP sessions. Preferably, these interfaces are across different Direct Connect routers on our side and on yours. And just so you know, by default, when you order a second Direct Connect from the same account, we'll shuffle the placement of that Direct Connect to another device. If this is being set up with link aggregation, that changes, right? Link aggregation remains on the same router. The next step up would be to configure these with site redundancy, maybe in the same home region, or maybe in a different geographical region. Just make sure that you have at least 2 VIF attachments. OK, so with this model, how do route advertisements work? The Direct Connect gateway does not support overlapping CIDRs of the VPCs. It also doesn't support inter-VPC communication. That is what VPC peering is for. The Direct Connect gateway is a central point for aggregating control plane, but operates each VPC as a singular entity. Here's a better example. Each VPC CIDR allocation will be advertised as is to the customer gateway. The routes from the customer gateway are also advertised as is. There's no route summarization or aggregation that happens, and each private virtual interface supports up to 100 route advertisements. Since there is no concept of route manipulation at this level, you'll need to make sure the total number of unique prefixes across all of these is equal to 100 if you are using propagated routes within your VPCs. This is because the VPC route table is also limited to 100 propagated routes. If you exceed this limit, you'll have unpredictable or inconsistent route propagation. Logical redundancy. I mentioned we would touch on some new features. A few weeks ago, we launched a new feature called logical redundancy. It's only available today in Equinix SV5, which is San Jose. And we will have this introduced into other sites in the near future. So, what is logical redundancy? Before logical redundancy, this is what a single Direct Connect connection looked like. Your customer gateway, a couple of patch panels, and an AWS Direct Connect device. If we did maintenance on this device, or if we had an issue, the whole connection went down, physical and virtual, regardless if your router was okay. Each virtual interface had one and only one BGP session, and the only way to get control plane redundancy was to enable a new Direct Connect. With the new logical redundancy design, we put a simplified aggregation device in front of the Direct Connect peering device, where the BGP control plane is terminated. And this allows you to terminate 2 BGP sessions on 2 different Direct Connect peering devices over the same physical Direct Connect interface. Now, you can use an independent /31s per peer, or you can use a /29 for the whole virtual interface. How does this change my physical redundancy? It doesn't. For device redundancy, you still need to order another Direct Connect interface. And you will need to consider terminating these connections on multiple customer gateway routers, your router. But it gives you the opportunity to maintain bandwidth and availability across a single interface. If we're doing maintenance, if we're shutting our devices down, if we have a problem, that shouldn't affect your connection. Currently, this is only available in Equinix SV5, and again, we are looking to introduce this to other sites in the near future. You can also verify if logical redundancy is available within your AWS console and also APIs. I'll show you what that looks like in just a second. This is a snapshot of the connections portion of the Direct Connect console. There's a new field on the bottom right, I've zoomed into it there, that says has logical redundancy. If this says yes, it means that you are connected to a logical redundancy-capable Direct Connect device. Again, this is only available in SV5 today and for new interfaces. So go ahead and take a look at that, and we'll make sure to post on the blog when new sites start becoming available. Here's a snapshot of the virtual interfaces section of the Direct Connect console, and this is where you can see that there are 2 BGP sessions on the same virtual interface. At the bottom of the screen, you can see that the AWS device ID is also different for both those sessions. So you make sure that it's actually terminating on different devices. So traffic engineering. Another question I get asked is how to control traffic in and out of AWS. This is especially relevant for customers who have geographically diverse peering points with AWS. In the past, customers relied on AS path prepending and more specific routes. For traffic going toward AWS, they used BGP local preference most of the time. While AS path provided a viable option for traffic engineering with within the same geographical region, it did not guarantee the customer preferred path with multiple geographically diverse regions. In order to understand how to control routing in and out of AWS, we need to go back to some of the basics of routing. With the show of hands earlier, I know most people, this will be not new. When a packet arrives at a router, let's say as it's leaving your VPC in US East 1, and it's on its way to your data center in Ashburn, Virginia, it has to make a decision on how to get your packet to its destination. If the router that's making the decision has multiple paths to the same place, then it will pick the best path it has in its routing table. In router terminology, this is usually referred to as the cost of the path, where the cost is always better if it's lower. The cost is typically derived from a series of decisions, such as the distance of the path and the speed of the path. For example, it'd be safe to assume that in normal operational state, from US East 1 to Ashburn, Virginia, would be lower and more preferred than the network cost to here in Las Vegas. So if you had 2 data centers, one in Ashburn, Virginia, and one in Las Vegas, one here, and both sites were advertising the same network prefixes, the default routing behavior would be to send the packet toward the lowest cost, Northern Virginia, Ashburn, Virginia. In this diagram, you have two direct connects to the same Ashburn location, split between at least two routers. And the network cost to both of these is the same, 100. This is called equal cost. And by default, we support something called equal cost multipath, which essentially allows you to load balance across like paths with the same cost. Now, if we introduce geographic redundancy and we set up another direct connect in New York, and this link advertises the same network prefix, but is much farther and has a higher cost, we no longer have a scenario for equal cost multipath. When the AWS Direct Connect network is deciding where to send the traffic, it follows, just like any router, a route selection algorithm. When traffic engineering and working with Direct Connect and VPCs, you need to consider two things. You need to consider the VPC's route selection and the Direct Connect's route selection. Let's cover the VPC first. When you set up the VPC, you define the CIDR allocation that the VPC and everything deployed inside it will use. VPC local routes are always preferred, even over more specific routes. For example, if your VPC is configured with 10/16, and you try to make a more specific route, static route, for 10/24, over Direct Connect to your on-premise, it won't work. The next place it looks is LPM, longest prefix match. The more specific route advertisement will be preferred. Then it's static routes in the VPC route table. Then dynamic routes. These are the routes that are learned from either VPN or Direct Connect when propagation is turned on in the VPC route tables. You don't have to use propagation. You can leave that disabled and rely on statics instead. From the propagated routes, we'll choose Direct Connect routes learned first, then VPN static routes, then VPN dynamic routes. Once the packet leaves the VPC and is on the Direct Connect router, the longest prefix match will be the first preference. Immediately after longest prefix, it will look at the local preference. This is key, as it's the best way to manipulate traffic for both ingress and egress to AWS. Local pref is followed by AS path, which also applies within the same Direct Connect location. This is why we say that local preference should be used to ensure consistency when dealing with traffic engineering. If all of these are considered equal, it will load balance per flow. So let's visualize this. Here we have a single VPC in US East 1 and a single data center, also on the East Coast. From the data center, we are advertising 172.16/16 across two private VIFs toward a Direct Connect gateway. Both of these connections are in the same Direct Connect location, and the first private VIF is advertising 172.16 prefix with 3 ASs prepended onto the route advertisement. The AS path attribute is used to help mitigate routing loops, as we're all familiar, as well as discover how many autonomous systems it has to go through to its destination. The second private VIF is advertising the same prefix, but this time it only has 2 AS paths prepended onto the route. In this situation, the routes both had the same prefix length, they had the same network cost because they were in the same Direct Connect location, but the green path had a lower AS path, which told the network it was the more preferred route or path to the 172.16 destination. Now, if we connect our geographically redundant location on the West Coast, and we advertise that same 172.16/16 prefix, it still will not be preferred even with a shorter AS path, as it has a different network cost because it's not in the same Direct Connect location. If we change the advertisement and make the route more specific, so changing the route from 172.16/16 and moving towards 117.16/24, the new West Coast path will be selected for routes that fall within that prefix range. You will see both east and west are green. This is because the more specific route is selected first, and the shorter AS path is selected for the less specific route, 172.16/16. Routes that fall within the /24 will be routed to the West Coast, and routes that fall outside of that /24 will be routed and remain on the East Coast. Okay, this helps if I can control the prefix length. That's not always the case. And this is where local preference and communities come in. So what is a community? You can read up above me, but I guess it's not above me, it's beside me. But essentially, it's a piece of metadata that's attached to a route when it's being advertised. This is similar to the AS path prepending. We first introduced community support on public VIFs, different than what we were just talking about, in order to manipulate the way we advertise routes that were sent to us. If you remember when we discussed public VIFs, by default, they're configured to allow bidirectional connectivity to any global public service. We also mentioned that you had the ability to change and limit the scope to continents, local regions, and global with the use of communities. For example, by attaching the community 7224.9100 to the routes you advertise, AWS will only be able to reach those IP addresses via the local region that your Direct Connect is paired to. AWS also applies community tags to the routes we advertise to you over these public VIFs. We do this to help you filter based on geographies you may not be interested in. If you're connecting to AWS in North America and you only use North America-based resources, you have the ability to filter routes that you learn from Direct Connect with the 7224.8200 community tag. Based on this filter, you can either accept or deny these routes into your route table. So in this case, you would probably do accept all routes that are tagged with 7224.8200. If you do not filter based on any communities and you just allow the default, you'll receive all the global public routes. On Direct Connect Gateway and any standard private VIF, so not public VIFs, when you're connecting to VPCs, the communities act a little differently. Instead of implementing route scoping, the communities are used to implement route preference. Remember, the communities are simply just a tag, like metadata, and this metadata can be used to trigger a change based on like identified routes. We have 3 communities that can be applied on a private VIF: 7224.7100, 7200, and 7300. There are no community tags attached to routes from AWS toward the customer gateway, toward you. Each of these community tags applies a local preference to the route being received by AWS. If you apply 7100, it applies a low preference. 7200, medium, 7300, high. The highest preference is preferred, and if all routes are equal, including the local preference, what happens? Balance by flow. Okay, so if we jump back to the diagram, all the prefixes are the same across all links. So they got that 172.16/16 prefix. Currently, the most preferred path is the one in green because it has the shortest AS path and is within the local region. Now, if we go ahead and implement the 7224/7300 community, which is the highest preference on the west path, and implement low preference community, 7100, on the east path, I'm able to engineer the traffic to prefer the west path without adding more specific routes. Here's an example of what a policy statement looks like in a Juniper router. This is the same from earlier. And this is implementing a high local preference community to the default route. This is the same example from a Cisco iOS. And both of these are available now when you download the configuration within the console. OK, so I'm going to go relatively fast on this one since there wasn't too many finance folks in the room. But this is actually a very common question. Basically, what am I paying for? If I connect over Direct Connect, who pays for what? I budget my networking separately than my applications. I need to prepare for that. There's two aspects of pricing. You have the physical interface, which is billed per port hour consumed. And you also have the data transfer out, which is charged per gigabyte. We do not charge for ingress traffic. It's only egress traffic. Data transfer out is dependent on the source AWS region and the AWS Direct Connect location, regardless of service. This is slightly different than how it used to be. A full chart showing the cost breakdown can be found at the link at the bottom of the screen, or you can simply search your favorite search engine for AWS Direct Connect pricing. For example, if you are requesting data from an EC2 instance in a VPC over a private VIF, or you are requesting an object from an S3 bucket over a public VIF in the United States, and your request is coming over a Direct Connect in Las Vegas, you will be charged 2 cents per gigabyte out, regardless of the service type, S3, EC2, DynamoDB, so on and so forth. If you're requesting data across the same Direct Connect in Las Vegas, but this time the source is in Ireland, EU-West1, then you'll be charged by the gigabit out for that individual site's pricing. So 2.82 cents per gigabyte. So there's a cost for running each physical interface, and there is a direct data transfer cost that is tied to the source of the data and the destination of the data. You are only charged for the outbound traffic. Here's a snapshot of the pricing page that shows the Direct Connect port cost. And here's a snapshot of the data transfer out cost matrix that shows the source and the destination of the data transfer. Again, this can be just found, just search for AWS Direct Connect pricing. What if I have multiple accounts? How does this work? If you have multiple accounts in an organization that share a same single payer account, none of the pricing changes. The only thing that changes is who's actually gets the bill for it. Instead of the Direct Connect account owner seeing the data transfer cost, the same price will be charged to the source account. The Direct Connect account will only be responsible for the physical interface port hours. If you're requesting data from an account that is not within the same organization, you will be responsible for the port hour cost for the interface, but no data transfer cost. The source account will instead pay for internet egress charges. So if you have a public VIF attached and you're accessing data from somebody else's S3 bucket, maybe a partner of yours, that partner will pay for internet egress. You will only pay for the port hour cost. Now, as a side note, there is a feature within S3, if you are the partner and somebody else is doing this, that you can enable requester-paid buckets. That flips this model, but it isn't on by default. OK, completely shifting directions here. I told you at the beginning that we would be talking about some use cases and new features and functionality. customers with Direct Connect are often connecting to data centers where they have DNS infrastructure. And a VPC relies heavily on DNS for addressing instances and services within the VPC. By default, the VPC uses built-in functionality to resolve local queries to public and private hosted zones. The default VPC resolver is configured with your VPC CIDR address +2. Okay, we call this the +2 address. This is a question I'm asked all the time. How do I manage the resources between the two? Here we have a single VPC, 2 instances in it. The VPC is configured with 192.168.1/24 as the VPC CIDR. I have a single subnet with 2 instances in it, both picked up IP addresses from my default DHCP, and I have a default DNS configured in my VPC, which means that it's basically 192.168.1.2 +2. Both instances were allocated dynamic host names from the VPC DNS, and we refer to each of these as 1.myvpc.com and 2.myvpc.com. I also have Direct Connect set up to my data center, which has been allocated the 10/16 address range. This is where I run mydc.com. If host 1 is trying to reach host 2, it will ask the local VPC resolver where 2.myvpc.com is. The local resolver will reply with 192.168.1.11, the IP of host 2, and it works just fine. Nothing weird there. Now, if client 1 in my data center is looking for host 2 in my VPC, it will reach out to its local on-premise DNS resolver, and since this domain is not hosted by mydc.com and it's not publicly resolvable, I will need to create a conditional forwarding rule that forwards those queries to my VPC. But this doesn't work. The VPC local resolver is not reachable from anything other than resources local within the VPC itself. To get around this, folks have implemented their own solutions by implementing DNS servers like Unbound running inside the VPC. And these are usually running conditional forwarders. The instance-based Unbound resolver can then be forwarded to star.myvpc.com to the local VPC resolver. This works like a charm and can work bidirectionally in hybrid DNS scenarios. But it is one more thing that you have to manage, configure, keep track of, pay for, so on and so forth. This is why we announced the Route 53 resolver service. With AWS Route 53 resolver service, you're able to place resolver endpoints inside your VPC that are reachable over Direct Connect. You can also place multiple endpoints in different availability zones for primary, secondary, and tertiary forwarders. Now, when an on-premise client queries its local DNS resolver for 2.myvpc.com, the on-premise DNS server can now configure conditional forwarding rules directly to Route 53 resolver endpoints. And Route 53 resolver will reply to the requester without requiring any mediator DNS forwarding instance inside the VPC. The AWS Route 53 resolver is also capable of conditional forwarding. Basically, the reverse of what we just discussed. Previously, this was not possible without running your own DNS inside the VPC on EC2 instances. So now, when a host 1 in the VPC asks where a resource is in my data center, I can set a conditional forwarding rule pointing to star.myvpc.com to my on-premise DNS server. Previously, this was all or nothing with the EC2 instance. And with conditional forwarding rules, I can keep all local routes local, and I can forward all other zones appropriately. Once the on-premise resolver receives the request, it can simply reply to the recursive resolver and onto the client. This makes resolving DNS between dispersed locations possible as a native solution. If you aren't the DNS administrator, make sure to tell them, because they'll be very happy with you. So far, we have gone through a review of the components that make up regions, availability zones, VPCs, and Direct Connect. We have also discussed connectivity options within a single region and across geographically diverse regions with the use of AWS Direct Connect Gateway. We talked about traffic engineering and how to manipulate the way traffic goes between AWS and your data centers. But what good is all of this if you don't go through the exercise of understanding how your applications fail as a whole? You may understand how Direct Connect fails, but what good is that if your application that relies on Direct Connect can't adapt to the new conditions of the failure? Our CTO, Werner Vogels, is known for saying, everything fails all the time. And I constantly come back to this when customers ask me how I think about redundancy and resiliency. When you are thinking through an architecture, it's easy to place systems into silos instead of looking at the system as a whole. Redundancy isn't just the network design or having the ability to have an EC2 instance auto-recover. These are obviously pieces of the puzzle, but not the system as a whole. You have to start with the application. Things fail. Is the application tied to a specific availability zone? If a single AZ fails, is the client able to move the connection to a different AZ? How does it do it? Does it rely on DNS? Is it targeting something that's distributed like the Elastic Load Balancer? Is your application in more than one geographical region? And does it need to be? 5 nines means the application can only be down for 5 minutes and 15.6 seconds per year. That's 0.9 seconds per day. I would argue that a lot of applications don't need this. Some do, a lot don't. Do you know what your organization's availability definitions are? With AWS, we provide constructs like availability zones, regions, and highly available managed services like the Elastic Load Balancer that can often increase availability without actually adding complexity and cost. The VGW is a logical construct. It's a redundant system in itself. But what is connecting to it? Do you have a single private VIF? Is it attached to a Direct Connect gateway? If you have multiple virtual interfaces attached to the virtual private gateway or Direct Connect gateway, you want to make sure they're coming from different physical interfaces, ideally from different physical devices on your side and on ours. Depending on your availability definitions, you may want to have your virtual interfaces originating from different geographically diverse Direct Connect locations. If you're using a partner or service provider to connect from your on-premise data center or branch location, you want to make sure you understand their definition of redundancy and resiliency. If it's an MPLS service, what kind of failover is supported? And what should you expect from a convergence perspective when there's a fiber cut or network event? If you have multiple fiber connections, are they diverse or do they ride through the same conduit? A lot of folks use Direct Connect as their primary path and have VPN tunnels set up in order to provide a backup path. This is a great pattern, but can also lead to some really weird, unexpected outcomes. If you're running 10 gigabit per second across Direct Connect and take a hard failure, but only have a single 1 gigabit per second VPN tunnel, what happens? In a perfect world, everything is running TCP and things just fix themselves, ramp up and ramp down, and operate a little slower. Usually, this is not the case. Make sure to consider how your applications fail. Failure isn't always an all or nothing situation. Sometimes a single application can fail, which may cause a total failure. Does your organization have a single point of failure that could cause all traffic to fail over at the same time, like a large synchronization of data? And if this happens, are you in jeopardy of congesting the entire Direct Connect interface? And if this happens, do you have the right processes in place to mitigate the issue at the source? For example, if an EC2 instance in a VPC starts blasting traffic over a Direct Connect, it won't do you any good if you block it on-prem. You have to mitigate it at the source. Here's a really interesting one that I come across all the time, actually, specifically with latency-sensitive applications. A device goes down in your East Coast path, all traffic shifts to your West Coast path. You have enough network bandwidth to pick up the slack, but you introduce another 100 milliseconds or so of latency. The application no longer works. The network failed perfectly. Everything converged, and the application's still down. It's not enough to put redundancy mechanisms in place. You need to understand the application flow and requirements, which can be super hard. Sometimes you don't have the hard requirements. Around latency and throughput is a big one. And that leads me to my closing recommendations. Keeping you in suspense. Don't rely on thought exercises alone. You have to test failure scenarios. And as things change, you have to test them again. Work with your application teams to understand their requirements and what availability means to them, what their requirements are. Verify your VPCs and workloads have the correct level of availability, and make sure that you have more than one virtual interface attached. This one's a huge one. If you're using a Direct Connect gateway, same thing. Make sure you have more than one virtual interface attached. And hopefully they're coming from redundant sources. Use communities and local preference to implement any traffic engineering. Don't rely on AS path in multi-site configurations. Local preference is the best way to gain consistency and predictability. And last but not least, a really weird one, but please play around with AWS CLI. If you're not ready to make that leap to play around with the APIs, this is a very, very easy way for router heads like myself to get introduced to the scriptability of AWS without having such a programmery interface. Check out the AWS CLI if you haven't already. So thank you very much. We're going to go into the hall for questions because I think this is going to get pretty packed.